Hello, hello, hello. Just working on some of the PowerPoint stuff. How can I help you? 444. Also, welcome to the group. We're working on getting the Discord. Okay, there's construction going on. It's all a process. Get this up. And let's get some absolutely banger songs going. Because if we're doing chemistry, we have to listen to good music. You can't hear it, though, because I'll get copyright struck. Okay, that's safe to move, so let's move that. Yeah. Oh. You explained in class the idea of the most acidic, lowest pKa proton. I didn't quite understand the XYZ thing. Yeah, so the XYZ thing is basically all I want to say is um, I've explained this so many times that it's like it's clear that something's wrong with it. But it's basically this picture effectively. So electrons resonate, and but the formula for the most part is the same. This is a cation, for example, but there's always some sort of like atom that doesn't have a double bond associated with it. And in this picture, it's a cation where the electrons can move over there, and now the cation is on a different carbon. And then this example right here shows us the same pattern repeats itself. This oxygen, single bonded to something that's double bonded, can also resonate. And so what I'm suggesting with my horrible, idea is effectively if you have an A single bonded to a B, and that's double bonded to a C, and you have electrons on the thing that's single bonded, and if I call this, whatever, this one, if when I labeled the number 2 atom, so if this is number 1, but any atom that is 1 away from it, or now number 2, so I went 1 away from it, and so I got to 2. That's a +1. If I get to B, and there's a double bond, the theory here, right, I'm oversimplifying it. The theory is that these p orbitals will overlap with the lone pair. And so this lone pair can go into those orbitals. And so to show it in a more, three-dimensional way, right, what I can do is I can take A and kind of put it on its side, and we'll put B here, and then we'll kind of put C back here. And so what's actually forming the double bond is that B and C have p orbitals that are bonding together up here. And so this is the, filled orbitals. And then here it's like, there's a little dotted line between these ones, and I should probably make it a little bit thicker where the bonds are. So here it is, there and there. And let's just make this a carbon and a carbon, and we'll make this, another carbon. And so when we deprotonate it and there's an electron pair on here, that electron pair, wherever it is, it's possibly sp3 hybridized, but this bond rotates. So it has it attached to, let's say there's something going forward and something going back. But and maybe I'm being a little bit unclear in terms of I could be drawing the hydrogen bonds as orbitals as well, but I'm focusing on these electrons here. They're not tied to the hydrogen like these are. These orbitals are not very interested in moving. They can. We'll find out later they can. But what we'll start with first is that the lone pair could move because it doesn't have a hydrogen holding it kind of to the carbon anymore. So it's a little bit higher energy, and so it's going to actually this bond will rotate so that these p orbitals align, and it'll send its electron density and mix. And so you're going to get more mixing of orbitals. And so in some ways, resonance is kind of scary for students because it starts to break down. Wait, I only thought p orbitals could combine with p orbitals. A lot of this is a lot more complicated than we're letting on. And thank goodness we have computers to show this to us. But what I'm trying to focus on showing students is to keep your eyes open for anytime you're looking at a question and there's a double bond, and you know we have whatever, two atoms associated with it. Heck, I think I can even do it in a chem drawing to be even prettier. So ka-ching. All right, all I'm saying is that this is a pattern in, oh, come on, whatever you want to call it. It's like whenever, and it doesn't have to be double bonds. You don't have to have it be two carbons. Now, granted, C is probably complicated, so that's why I do ZXY, don't I? Oh, boy, no, I forgot all about ChemDraw, no. Also, would the recording of office hours be considered solo? Yeah, I would say so. I would say if someone came to me with questions about something, I would be okay with you guys coming back to look at it, because I'm hoping to create a resource that's like these videos you are going to, effectively. Like, you are going to other videos and learning about this pattern. Why can't you go to your teacher's own videos about those things? I'm not yet convinced why that isn't something I would allow. Because what's not going to be on the test is what I go through exactly in these videos. It's related. You use the same skills, but it's not going to be the same problem. But again, the pattern is just like, this is what I'm looking for. And in my head, I go through in some ways, and I'm kind of thinking like these bonds stick out to me as a person because I've done so much of them. And so whether it's a cation that's an empty p orbital, no, it's more orbitals. But and let me make this a little bit clearer as well. So it's like, okay, there's this, and when we pull it up like this a little bit, so now we're getting a little bit more of that image to it. Again, these are filled orbitals that are aligned, and so we'll put them in, ka-ching, ka-ching, and we'll say, like, you know, they're connected. Oh, ChemDraw. Oh, no. Gosh, what if I could draw? I think you can, but it's not as nice. All right, those p orbitals are aligning, and then when this thing is sp2 hybridized, as I look at it, that's a pretty broke look at it, but again, there's kind of like one going there, H and H, and let's even make them look a little bit better. And so this orbital here is, this is empty. And whereas these are full. And so there's more space for these electrons to go and live in. And so that's the cation, where it's an empty orbital, but in the same kind of idea. It's a little bit different looking. Oh, wait, yeah, we want to leave that. But we can also say, what if it's full? And it's probably not going to be a p orbital in this case. Now we would have a sp3 orbital going this way, sp3 orbital going that way, sp3 going that way, and this is just ugly. So let's see if I can make it a little bit prettier. So what we're trying to think about is how there's this orbital that's in the page, and when I think about a typical, what you're used to seeing, when you look at sp3 orbitals before my class, it was pretty common for you guys to draw something akin to this. That's an approximation of a pretty good, oops, get back up there. It's a pretty good look at the sp3 shape. And so I want you to see that as I place it back over here, all right, this orbital is, I gotta do it a little bit cleaner. So I'm gonna rotate it just a little bit to match that bond. And so there we go. So boom. And then this orbital is kind of going back into the, and then this orbital is a little bit bigger as it's coming out at us. Gosh, I'm not an artist, but we're working on it. So not the prettiest thing yet. Maybe I need to bring this down a little bit, and I need to send this one to the back. Gosh, it has been a second since I've done chem drawing. Oh boy, what are we doing? It doesn't matter. Maybe you get the idea. I don't know. You kind of keep an eye on what you're used to, which is the sp3 that you came in with some knowledge of. And so I'll kind of put that maybe in, let's say, red. Are the different sides of these orbitals? It is a perspective thing. It's a perspective thing. And it's me just trying to show it to you in some ways. Like this was overdoing it. Really, in some ways, that this green one should be a little bit, this one should be the biggest. And that's what that would be. That's better looking in some perspective ways. And then this one is still kind of messy, and I haven't quite finished it. Because I want to say, what I want to say text-wise here is that the sp3 shape remains for the most part. It's a little bit different because the lone pair is a little bit more diffuse now. And so here we have like an H is at the end of this orbital. And let's just add all the color to this and just kind of make it its own little plop of an image. Okay, so like there's this orbital is the, and so I can go in here and say pink is wedge. Oh wait, I think I have to do a separate one for it to hold the color that I want. Yeah, dun 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 dun. Dun, 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 dun. And so this one here is yas. And so that's kind of tucked behind there, and even this orbital itself I'm trying to represent as still full, still connected. And so in the back of our head, we're kind of thinking about this shape here, where we have a paching, and then, oh, I don't love that, but I also sort of confused because I read that you couldn't have resonance with an sp3 hybridization. I could have misinterpreted. You can't have resonance with two sp3 hybridization. By this kind of like let's see if we could find somebody who's drawn a picture for me already. Bum, bum, bum. Wondering if my stuff for my lab forms are in. Yes, it is. It should be good. We're going to be working on that. So my mom right now is not able to do her part of the job until tomorrow night. Partially because I was late on my part of the job. So we're still working on it. But let me keep seeing if I can find a good image for this. Because there is a missing part of this argument here where once they mix, they're not SP2 or SP3, but they're somewhere in between. And so it's a little bit beyond maybe our quote unquote pay grade. And so what we want to focus on is that these orbitals are able to align at least a little bit in space. And so we want to look for the overlap that's possible, and yes, they mix and become something that's not like, again, let me try to make this point with an example. So when we look at this molecule here, a very classic one we've seen before, we don't say that this bond is a single bond. And we don't say, let me see a second, and we don't say that this bond is a double bond. We say, well, these bonds are somewhere in between a single bond and a double bond. And so oftentimes we draw something like this, and then we'll put in, I don't even know if we can do it in ChemDraw. I can at least draw it in, but we'll often like draw a dotted line to connect them, to say it's between one bond and two bond, because our orbitals are mixing and they're not all perfectly aligned, and there is a little bit of inalignment to them. And you know, we could draw a picture where we force the O to go sp2 hybridized, and we force the electrons that are moving into a p orbital. I could expect you guys to draw that. I could expect you to draw this sp3 one where it's like, it's starting to get into hyperconjugation world. We don't necessarily know it yet, but to bring it back to something that's useful for what this exam is looking at is just that when you talk about stabilization of an anion, I want you to be able to look at this pattern and see that those electrons can go via an arrow into this bond, and then these electrons can come out and go here. And so you are spreading that via resonance. And so you want to be able to, your eyes want to identify that. So I'll leave it there and say it is more complicated. You know, over here I kind of realized it's like I'm starting to explain more than they need right now. We're going to keep working on this as we walk into exam 2, right? All of chemistry class is always gets more complicated. But for now, let's just start training our eyes to look for when you have a anion, and I know this is not well established yet, but it's like when you have an anion and you have a single bond to a double bonded carbon, I want your eyes to look for that. So, question, S is stronger than P, so why is hyperconjugation more stable? So, let me see. You're talking about hyperconjugation in terms of stabilizing an orbital, I imagine, or stabilizing an E1 cation? Let me make sure I'm looking at the right learning objectives a second. At the sunrise in my eyes, in my eyes. Awesome. Okay, great. So let me make sure I'm looking at the right learning objective and answering something that is somewhat helpful. I guess, and I have to ask, I'm not 100% sure yet if I get what your question is asking. And so I'll start to explain hyperconjugation and see if your question comes more clearly to me as I'm going through it. Great. Okay. So hyperconjugation basically says that when we think about these orbitals actually forming for getting these leaving groups to leave, we have to think about things that stabilize a cation. And so this is a subtle change in our perspective where we're used to talking about how to stabilize an anion. The Serhi, right, is a way to explain how to stabilize a anion. But in this case, what we're looking at is how the heck do you stabilize a cation? And so if I look at, if I leave it like this, where it is a carbon completely by itself, and it has gone sp2 hybridized, the degrees, if I kind of zoom in on this, which I can't zoom in any further, but is there a way to annotate even my screen, maybe? No. Okay, well, let's just do this. Like, the angle from here, I want a different color. Come on, come on. Listen. Is it maybe not just going to work? Okay, well, what am I going to do then? Oh, ChemDraw. You're so old, ChemDraw. When are you going to get your upgrade? So I think I can do it with just bonds. So what I want to show here is that it's a 90-degree angle. The angle that I'm trying to show you is that, let's do it this way. Let's make that one yellow. So the p orbital is right yellow one going up and down, and the red orbital is the actual electrons that exist. The red one is the electrons that exist. The yellow one are the electrons that don't exist, but there's space for them to exist. There is a home that they could exist, but they're not there right now. And so this example is no hyperconjugation. In this picture right here, there's no hyperconjugation because we are completely orthogonal to one another. We don't have anything aligning up. And so what's the difference is if I kind of come back, if I come back over here and I say, okay, let's change it a second. Let's start to stabilize it a little bit. And so I'm going to take the easy example, or at least easy to draw, and I'm going to put this C here. I'm going to say, what if now we have this H? So orthogonal, hopefully I used that right. I'm pretty sure I used that right. Yeah, great, I did. About time. It's just means that you're having right angles. Rather than it being parallel, orthogonal to one another. They have to be 90 degrees. And so this is that idea of like, if you have py orbital and px orbital, they don't interact very well. I mean, especially when they're on the atom axis, they just kind of go right through each other. And in this way, it's the same thing. But when we bring in a carbon instead of a hydrogen to these things, that's pretty ugly. So let's kind of put it over there, out of our way. We know bonds rotate, single bonds rotate. And so in here, and let me do some expanding a second. And so if we go back into our head a little bit and think about how this orbital formed, oh, that's not right. We think about actually how this orbital formed, and that's not, I mean, it's accurate enough. So we brought a 1s orbital from hydrogen, because again, if I look up the electron configuration for hydrogen, this is all that's there. And then suddenly I have an sp3 orbital from carbon that's here on carbon. And so these are mixing, but the electrons that are in here, they are in line. They are parallel to the other orbitals. And so now, whereas before my orbitals were orthogonal and they didn't mix very well, now when I have a CH bond coming up and parallel to my theoretically empty space, these electrons are like, huh, I can I'm kind of spread out there. I have more room to spread myself out. And so again, the orbital doesn't necessarily exist. It's the absence of an orbital. But the fact that there's space there for electron density to interact with, that is what is effectively attracting this kind of bond, is kind of being pulled towards it in a way. There is positive empty space here, and electrons are like, and again, let's focus on what are the electrons actually looking at, right? There is a big old pack of protons right here. Because something was picked off, because a leaving group just left, there is protons, extra protons here without extra electrons to stabilize them. And so this bond is partially like attracted, kind of maybe tilting is the wrong word because it treats it too much like a particle. But the wave of electron density is attracted to this orbital. It's starting to kind of interact with this area a little bit. This is an open area for the wave now to, the wave function is being adjusted by this cation behavior. But again, that's even getting a little bit too crazy into what we need to worry about. So I'm still not 100% sure how I want to answer your question, because I would say S orbitals are better at stabilizing things. Like if I compare, 2s versus 2p, certainly the 2s orbitals are more stable because the electrons are closer to the protons, and so they're more stable. But I don't think that's necessarily your question. Hyperconjugation is resulting in S and P mixing. In this case, you have sp3 orbital. That's what I have here. And it is attracted to cations, theo, LUMO, and theoretical is what I should write that out. Theoretical, LUMO in yellow. Because protons here with no electrons. Well, I should say with less electrons. Since leaving group left. So let's pull that out, pull this away. And so this is where our pay grade needs to be for this exam, is just to start to see that, oh, okay, how do you know what the theoretical LUMO is? Because what I'm thinking about is the idea that when electrons leave something, so let's think about what happened here. So we had a carbon that was here, and well, let's go over a second. So what I want to do is kind of go back in time a second and say, okay, this carbon was either connected to, well, to keep it somewhat simple, we'll say it was either connected to a carbon or a bromine. And so what does the molecular orbital for these things look like? Well, why don't you just work the way I want you to, Kendra? Is it here? Ha! Got you. Okay. No. Okay. So before the bromine left, this carbon had 4 sp3 orbitals. One of them went to, which I'm not showing here for sake of ease of use, one of them did go to this carbon in the red bond. We won't talk about that. I can show it really quick. CsP3 has this level. On this level, CsP3. And then down here is, on the same subject, can you explain how you ranked 2 things for the practice exam 20A using MO theory? Let me get to that in a second. I love that question. So here it is, CC sigma bond. So again, this one is the simple one. So this C connected to, let's put a C here and make it pink. But that's not involved in the mechanism, or at least that's not the mechanism we're told. And so we're not really super concerned with those orbitals. But, you know, that's kind of what it looks like. And we also know that by creating this orbital, we also created the sigma star bonding orbital. And so if we go back here to the bromine and the carbon, so okay, one of these is connecting it to the carbon, and so 3 is left. 2 are combining to hydrogens, and 1 was combined with a bromine. And so the combination of this will kind of say, all right, depending on which direction we look with this orbital, these are now sp3 and sp3. And so let's start color coding some things. And so if we go to our hydrogen, although our hydrogen is a small orbital, it keeps its electrons fairly close to themselves. And again, granted, we can find out, we can ask a computer to help us with it. We know for sure that it's definitely not at the same energy level as the carbon. It's not the same energy level as the sp3 for carbon, but it is overlapping in some way. But let's just say that the hydrogen is a little bit maybe more stable than the carbon in this case. And we can do another example where it's not. But we basically will say, okay, so again, these things form some sort of reason why these things are bonded with each other. And so hydrogen brings in its 1 electron. C is closer to bromine because bromine is more electronegative. Well, I'm going to say, we're going to look at that one in just a second. It's going to be way further down. So again, here's this 1 electron, and let's see, there's that 1 electron. And so, oof. They basically form, this is the CH bond, those 2 electrons there. But when we think about bromine is fairly electronegative. So we're going to say, if we put H here, for example, with the electron that's actually bonding with it, bromine has a lot of protons and a lot of space to put its electrons. And so this one is going to be even lower in energy. And so now we have a fairly long stabilization journey for the carbon. And so, and this overlap is bad. And so the amount of stabilization that the bromine is getting is fairly good. And the carbon is actually pretty happy. Its electrons are like, wow, I've never seen this many protons before. And so as we go down here, oops. Let's try this instead. And so again, we have 1 electron here, 1 electron here, 1 electron there. Oops. And 1 electron there. And so what I want us to notice here is that these electrons are no longer here. The bromine and the carbon bonded, and so now they're here. They're in the bond. This carbon and this hydrogen bonded, and so now they're in the bond. And so when I'm, oops, I shouldn't have deleted them. And so now the question is, okay, if something is going to break. As these molecules are colliding with one another, we might be like saying, well, look at these electrons. They're more stable, so they're not necessarily going to be more reactive. Wouldn't it be these that would be the ones that would break? But pause for a second and think about what I'm missing over here. To actually break this bond, I need to fill the sigma star, which in the same way I get stabilized, I would also have to get destabilized by the, and so this would go up a little bit here, and this would come down a little bit here. But you're going to start to see that, well, what's the LUMO? Is it the CH bond breaking, or is it the CBR one? The lowest unoccupied orbital to smack into and to start breaking apart the CBR bond. This one is going to be easier because the bromine is more electronegative. So the LUMO, how much higher it is than carbon, it's actually pretty close to carbon's energy level, whereas the LUMO for the CH bond is a little bit higher necessarily. And if hydrogen is theoretically less stable than it, and it's up here, well, this still raises it even further up. We know for sure bromine is lower down, we know that these don't overlap well. So regardless of where we really choose hydrogen is, wherever we choose it is, this LUMO will always be slightly higher in energy than the CBR LUMO. So I'll put that in. This is the CBR LUMO. And this is the CH LUMO. And so as these things are smacking into each other, so H falls off. No. This is a Br falling off. This is the E1 reaction. So Br is a good leaving group because it has a lower LUMO. Yes, it has its LUMO is lower and it's unoccupied. And so if electrons start to fill it, because electrons want to go to just like we fill up electron orbital diagrams, you don't fill up over here first. You fill up where it's the lowest. That's what electrons tend to go downhill in energy. And add to it the fact that this is not a good bond. These orbitals don't overlap well. This thing wants to take these electrons. Because look, it's like when these electrons leave and go to, and before this electron's like, oh, I don't want to go back to carbon. Why would I break this bond and send my electron back to the thing I formed? Bromine's like, nah, electrons, come with me. As I leave, I'll take you with me. We'll go together. And so the electrons don't go back up to carbon. They leave with the leaving group. So bromine is a good leaving group because it has a lower LUMO, and the electrons after bonding are more similar in size and location and energy to the bromine group. And so when they leave off, that leaves us with, well, now we have a carbon that is sp2 hybridized, and it has to have an empty orbital somewhere, where now we have a carbon that is sp2, and it has 3 sp2s. You know, this first one is maybe the CC bond, and then we have 2 times the CH bond. But what is higher in energy than an sp2 orbital? And remember, these are filled. These are all filled orbitals because I'm getting away from a good picture here, so let me get back to a good picture. Right, there's electrons here, 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 and so these are all filled with the electrons that are bonding. But what would be higher in energy would be the empty p orbital, because we left it. The bromine's like, nah, sucker, these 2 electrons are mine. I'm taking them with me. I'm not leaving them with you, carbon. I want them. And so it leaves with them, and it leaves behind the LUMO that I can answer your question with. How do I know that the theoretical LUMO is an empty p orbital? Because in the MO diagram, freaking bromine was like, if I'm going to leave, these 2 electrons are like, you're leaving? Well, crap, we don't want to go back to how we formed a bond, because we don't go up in energy as electrons. If we're forced to leave, well, we do go up in energy. You know, we got smacked by some sort of collision, provided the energy to say, okay, we can actually, yeah, we don't, it's a little bit maybe kind of confusing you because we do see electrons move up in energy, but this is why you can heat a reaction and get things to happen where you collide it and boom, these electrons move over to bromine and they leave and you no longer have this and this and this. Now you have a Br minus floating away and it's getting stabilized by the solvent. Oh, that's why I bet. So that's how I could explain it. It's like this is being stabilized by a solvent. And so now the electrons do fall into it. The electrons that were here are like, whoa, check out this solvent pulling on this energy level, bringing it down. And so they do actually fall down into a lower energy state. It's solvent effects. It all kind of makes sense, but it's very complicated to stitch it all together. And so it goes off as a Br minus stable by solvent. But it leaves behind, you don't stay sp3, right? The carbon is going to immediately say, oh, I can better stabilize myself by making everything sp2, 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 and I'm going to spit out the empty p. Why? Because sp3 is only 25% s, which is the better orbital, when I can have sp2 would mean I'm 33% s. And so it just hybridizes. It hybridizes to the most s character it can. And by spitting out this empty p orbital by saying, well, there is no p orbital, this yellow one doesn't exist, there's no electrons here to mix, so I'm more s character now. Yay, I like that. I like being closer to my protons. So does that kind of help you answer the how do you know where the theoretical LUMO is? It's looking at the bonds that are possible, knowing what the weakest bond is, and we can treat it pretty simple in terms of saying that typically it is the electronegative atom, big things that are not like the thing they're bonded to. If I go back to my class slides, for example, be careful not to show student data. Bah, 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 bah. So this was part of my day 5 PowerPoint. Right. Observe heteroatoms and bonds and recall these things. This me showing you this was not as good as I could have done it. Obviously this like whatever much more long-winded explanation probably makes some more sense to you now. How I'm trying, or sorry, not here. This one here makes a little bit more sense as to why these things tend to result in a bond breaking and some sort of LUMO forming due to hybridization readjusting. But this is what my eyes are looking for. When I'm starting to think about structure and reactivity, I'm naturally drawn to heteroatoms connected to iodines, bromines, oxygens, nitrogens bonded to carbon, because those orbitals are slightly different in terms of their energy levels and where electrons want to go in terms of lower energy or higher energy. So on the same subject, can you explain how you rank the two things in the practice exam 20A using MO theory? So let's pull that up a second. Okay. Oh boy, oh boy, oh boy. So let me see. 20A. Okay. So file uploaded. Provide all the requested information as you analyze different aspects of the following reaction. So provide a completely fully labeled molecular orbital energy diagram for the first interaction between the two molecules. Be sure to include in your following diagrams labeled reference lines, name the HOMO and LUMO, and label each clearly. If HOMO or LUMO results from mixing of atomic orbitals, be sure to show this mixture and name the parent orbitals. One can imagine the molecule on the left acting as an acid in two different ways. Compare each and choose the correct LUMO based on your diagram. Hint, the amount of overlap and stabilization between two electronegative atoms, oxygens, is very poor due to electron repulsion. Okay, great. So we're basically going to say, and in the possible, well, let me see a second. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . Okay, great. So we have these two molecules interacting, and the kind of the theoretical interactions that are already happening. Where are the electrons going to be in these interactions here? Well, wait a second. Let me see. What are they showing here? Okay, I get what he's saying. Okay, so what we're basically looking at is first we want to look at, let's snip this a second. Thanks to my new things. Okay, great. And let's do a new one. Okay, so we have these molecules and we have this. We're going to get here at some point. Oops, wrong one. Okay. So, let's open this all the way up. So, okay. So, let's kind of analyze these one at a time, and let's start with the easy one. So, this one to me is the easy one. Why is this the easy one to me? Because, okay, we're looking at dimethyl sulfide. So, dimethyl sulfide, let's get a Wikipedia article up for this. What is it? It's a liquid. Oh, interesting. Okay. Okay, we've got DMS. It's a thioether. Let's pull this one over here. Oh, I want to see it with lone pairs, though. Show me an image with lone pairs. Nice. Okay, so great. Let's cancel that. And so it kind of reminds us here, it's not a great picture, but there's lots of different ways we can look at it. But it does have 2 electrons on the S. And so what I'm trying to think to myself is oh man, I can't see what you guys are saying. Yoink. Okay. And so there is electrons. Boom, boom. Boom, boom. And I'm trying to think about, okay, so what's happening in here? Maybe there's like some sort of possible LUMO character here where I can put electrons on sulfur. So I'll at least theoretically leave the door open for maybe this could be something that accepts electrons, because sulfur, well, let's look it up a second. How electronegative is sulfur? So let's look up electronegativity. Electronegativity table. And let's find a good source. Don't trust that. That looks like more trustworthy. Okay, so we'll pull this out a second and we'll say, yeah, sulfur is electronegative. Oh, wait a second. This is not a very interesting bond to me. They're not very different in electronegativity. Sulfur and carbon are pretty similar, so it's like, okay, so I'm not even thinking that it's going to be particularly good at accepting electrons. There isn't a lot of partial positive on here to attract a nucleophile. So I'll be like, okay, nah, not very interesting. So then I go back to my PowerPoint. I think to myself, so this part of this is, oh, come on. Oh, right. I couldn't do that here. I'm limited. And so this is, when I was looking at this molecule, let me try to make sure our images are kind of together here so we can kind of see where the logic is coming from. All right. So the thing I'm boxing over here, right, this is the SCH3. And let's make that bond just a touch bigger. All right, there. So that's where it is. These are stable, low energy electrons. The bonding things for these, the where these orbitals are, right? If I think about like the general, if I'm just thinking about sulfur CH stuff and energy of electrons on here, the sulfur, oh, come on, the sulfur and the carbon, pretty similar electronegativity. Yes, they have some difference in orbitals, but overall bond pretty well. They're overlapping their sigma bond, so they're down in energy. However, the sulfur also has not these bonding electrons that we see here and here, but it has the non-bonding electrons here. Oops, come on, give me some color. I want some color in my life. So they're there and there. These are ones that are not connected to a carbon. And so, yes, they're still connected to electronegative sulfur, and that's all well and good, certainly, but oof. And certainly that's oof. Try one more time. Yay! We're doing it. Okay, cool. So we come back here, and I'm like, okay, we now have a... These are the non-bonded sp3. And let's look at sulfur for a second. Sulfur electron config. Right, these are 3 S's and 3 P's, so they should be higher in energy than the C, but again, add in the fact that it has more protons, and so that would stabilize it. So a couple of factors here. I would like to eventually add some computation to this work through Avogadro and have students work through it. Maybe, you know what, I'm going to stop talking. I will stop promising things until I actually have them. I see so many possibilities. Anyways, focus. So, what I'm analyzing here is, in my opinion, what's most interesting about this molecule in terms of reactivity is these lone pairs seem to be kind of the most interesting part of this molecule. The sulfur and carbon is not interesting because there's not a big difference in electronegativity. There is a difference in size, and so that could be something to think about. And... you know, there is, but there's not a lot of like electronegativity pull going on here for us to do anything. But in general, my first thought is the lone pair is a more high energy because by bonding to carbon, it must be lower in energy. So let me write that out a second. So the electrons in the... and let's, the electrons in the SC bond are from S 3S 3p hybrid with carbon. And again, when we look at, all right, these are now the 2 S's. And so the orbital, or the, and so the, okay, atomic hybrid, let's just say AO, atomic orbital from the hybrid with the carbon's 2SO atomic hybrid. And so the MO must be lower in energy than the lone pair S, or sorry, yeah, the lone pair sulfur 3S 3p that gets no bonding MO with carbon. And so that's how I'm able to say with a good amount of confidence that by, we almost need to grab it again a second. How many times have I done that? Where are you? Where are you, Sid? Come on. Oh, no. Mm, 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 mm. Of course, of course. And thinking. I'm still trying to get this to come in right. Okay, great, good enough. So again, that's what I'm kind of seeing here when I look at this thing. I am very interested in, I know these electrons here are high in energy. Everything else about this molecule, not super interesting to me. Over here, though, what's interesting about this one is definitely what immediately should draw every student's attention is something they've seen before, which is the C-double-O bond. This is something that's been reactive before. We know that when we draw the C and we draw the O, well, let's do it better than this. When we draw the C and it has its orbital, and then we have the O and it has its orbital, there is the sigma bond that's forming beyond these two, as well as there is the slightly higher in energy 2p orbitals, which aren't quite as stable as this one here. And I think, well, we even need to bring it up just a little bit more. And typically a little bit lower in energy than the anti-bonding one. So it's a little bit messy, but we know that there is 2 in the sigma, 2 in the whatever. And if we were going to interact with this bond, oh wait, no, it has to be lower. So this does have to be down here. So let's make it a little bit clearer. So let's put it there, and let's bring you down. Oh no, get out of here. And let's bring you down, let's bring you down. Okay, so CO bum, 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 bum. Sigma bond, and then the slightly higher energy p orbitals, which don't overlap quite as well. Oh, well, that's not right either, but we're getting there. So boom and boom. Okay, now we're looking at it. So stable there, and the LUMO for this is going to be here. That's our LUMO. Now the question is, what about over here? Is there something interesting going on here? And that's what he's trying to hint at here. Hint, the amount of overlap and stabilization between two electronegative atom, example oxygens, is very poor due to electron pair repulsion. So what he's trying to clue us in on is that if we were to add, well, what are the lone pairs here, right? Oops. All right, this is a tricky question because he's bringing in a molecule that we have not seen a lot of this functional group around. And so in reality, there are electrons here in orbitals, here in orbitals, here in orbitals, and here in orbitals, going on dashes and wedges, dashes and wedges. And so these orbitals are pushing against each other, and we don't see that because all we're asked to describe is, okay, I've described the CO bond here, but the same O must be at the, oops, come on. So let's put that down there. And so now we're going to have an O at a similar level because these should be fairly equal-ish in energy. They are the same element, so they should have approximately the same stabilization. But the amount of stabilization we get from this is apparently not very good. So we go there and we go there. And so now this LUMO is higher in energy than this LUMO. And so this LUMO is more accessible. And they're trying to convince us that the reason why this is the way it is, the reason why these don't overlap as well as we might suspect, where we might want to go in and say, oh, it's an O connected to an O and they're the same shape. Let's do these gigantic drops in energy, these gigantic increases in energy. But what's important for us to realize is that if the atoms can't get close to one another, if the orbitals can't overlap because they're pushed away by the electron lone pairs hanging out kind of around, Well, we'll never get good overlap, and you need overlap to bring these things down, to both raise and lower things. So the answer was on the same. Can you explain how you ranked the two things for the practice exam on 20A? So yes, it's basically that O is, let's look at our electronegativity chart. O is more electronegative than sulfur. Yes, 3.44, 2.58. So the O is the most one. And in this case, right, the 2p that's forming the pi bond, they're showing us the pi bond interaction. They're not even showing us the sigma. And it's not wrong if you show the sigma. You have to show that the sigma is more lower in energy than the pi. I won't necessarily grade you on where it is in relation to other things necessarily, because again, more of a computer's job. And also not really worth memorizing, I don't think, because it's going to change for every molecule. But so that's why O is the lowest. Then sulfur is the next because it's at 2.58. It is more electronegative. And then carbon here up here is 2p. And again, they're showing us the sp3, which has more s character. And so not only is it more electronegative, but it has more s character. So that's why it's going to be a little bit lower. Whereas the LUMO that we'd considered, that's something I didn't make very clear in this example yet, but like in the answer key, there isn't even a consideration of the sigma part of the bond. No one's even looking at that because we don't. It's like if you're going to interact with a carbonyl, you interact with the double bond. So we're only going to draw, interesting stuff about the double bond rather than worrying about both the single bond and the double bond. I did it because it's good to remind you that it's there. But they had us compare it to, well, what else on here is reactive? And the hint was to basically draw attention to that. Because what else can I look at? The CH, the CCs are not interesting to me. The CHs are not interesting to me. The C-double-O bond is really interesting to me. Even the OH bond is interesting to me. I think there is possibly another orbital diagram you could draw where it's like, well, I wonder about, let me add this in, or let me adjust this one here. So let's kind of look in. All right, if you wanted to and say like, well, can this thing be an acid or something? Like, could that happen too? Well, where would that go? So again, we'd have a O, sp3, so it would be O, sp3. Where is that level at? Let's put it wherever this is. So it's right about there. And so I'm going to approximate it out to here. And then again, you probably already know this without looking at it, but hydrogen is less electronegative than oxygen. So you can grab this one and let's even make it, can I make it white maybe? I've had my fill. Okay, so we'll bring this one out over here. Ka-ching, ka-ching, ka-ching. And the H has to be higher. So here is the H, 1s orbital that's bonding with it. And so now when I come in with my paintbrush and I say, all right, this is bringing one electron, this is bringing one electron. And so, boom, it goes down a little bit and this goes up a little bit. And it goes here, here, and here, here. But because the 1HS is, and even in relation to, well, wait a second, where is carbon in this relationship? Well, carbon is at 2.55. It's even less electronegative than carbon. So really, I need to bring this up even further and say it is up a little bit higher. It doesn't have many protons stabilizing it, and so this thing does form a not very stable bond. And I'm sure this is a labile proton to some degree. But what we want to think about is to get to this LUMO is actually kind of or I wouldn't even call it a LUMO on this reaction because it is higher in energy. So if my 1s is higher in energy, then, and I think I overdid it a little bit. I kind of cooked this entire diagram a little bit, but it's a little bit too high. But once again, we have an empty orbital that's just not the lowest energy one. And so electrons are bumping into this orbital, and a little part of them are probably being pushed away a little bit by the electron density. Well, maybe not. I mean, how would you describe that then? Bum, 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 bum. Well, it is, I guess, higher in energy, I guess, is enough of a statement to say. And so the lowest unoccupied molecular orbital is due to these O's not overlapping very well. And again, we're kind of told due to electron pair repulsion. So that is how we are figuring out where they were. But it does require this hint to say that when we hear this, the amount of overlap is very poor. That to us means that how much they're interacting is not very big, but we know they're the same size. So this isn't a size issue. This isn't a bromine issue where bromine is lower in energy and carbon is higher in energy, and it's just that the orbitals can interact, but there's not a whole lot of overlap overall when considering it. This is two orbitals that really should overlap well. They're the same size, but because of the electrons they bring with them, and they have two lone pairs that are not connected to atoms, but are just floating kind of more in these freer orbitals, those don't allow the orbitals to come together as much. And so there's less overlap. And if there's less overlap, you get less overall space for the electrons to be in. And so the amount of stabilization you get by, well, at least now, like what's the difference again, is that when we break this thing apart and we go back to being by ourselves over here, it is less stable because it doesn't have the other set of protons to stabilize it. So it is like, okay, I would like to be here because at least I have now two oxygens stabilizing my two electrons. Whereas if I put these electrons back and break them back apart into, gosh, one day I can do this. Yonk, yonk, boom, 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 right? If I bring those electrons up and break them back into their pieces, and they go with their atoms, now it's like, well, only one thing stabilizing you. So that is how I would say I would work through reasoning through. Start with the easy molecule. This one to me was easier to me to reason through what it's probably doing. This one was a little bit trickier because I was attracted to look at the carbonyl first, but certainly I'm like, these are peroxy acids. And only by doing lots and lots of chemistry would I be like, oh yeah, of course, like I know these things, and we'll look at them later on in the course, but he's starting to hint at there's more going on here, and if they don't overlap well, if the orbitals don't, if the wave functions can't get close enough to each other to overlap, you don't get as much stabilization or destabilization. And then just fundamentally, O's are the lowest in energy, versus the carbon must bring up the LUMO. The LUMO must be above the carbon 2p. And so because carbon is less electronegative than O, we already think, well, how, depending on how much this can go up is limited, whereas carbon just has to go up a little bit, but it's already above O. So, okay. C is closer to bromine because bromine is more electronegative. Is it actually closer to it? I would say no, because there's too many electrons in bromine. It's basically like, let's look at bromine's electron cloud. I'm not sure how to like really describe it in a way that's meaningful because these are all wrong. Oh boy, Adam. Like it's hard to get a carbon and a bromine close to each other because bromine be packing electrons, and then the other thing would be whereas the C connected to another C has less electron repulsion, again, of the electron cloud, of the many, many things it's bringing with. And so H falls off. This is acidic. Not necessarily. I think that example before was like, no, it's the bromine that falls off because that would be the, that LUMO is more accessible than the H is accessible. And that orbital overlap is pretty garbage. And then, so bromine is a good leaving, and then so bromine is a good leaving group because of the lower LUMO. Yes. Question, cis trans versus ZE. Only use ZE. So the learning objective is super clear in terms of, it says, the learning objective is alkene is EZ. Cis and trans will come back, but don't worry about it right now. It will come back, but we're not worrying about them right now. Are there any other examples where the sigma star MO is the LUMO as opposed to the pi star? Would this only happen when there are two very electronegative atoms that create a sigma MO? Are there any other examples where the sigma star MO is the LUMO as opposed to the pi star MO? Would this only happen when there are two very electronegative atoms that create? Let me think for a second. Well, I think another one would be to consider is this a good example? So it's like, what if you had this molecule? Oh, it's a little funky, but I think it would work. I'm seeing if this is actually real or if I'm just making it up. Because I'm probably just making it up, but it's more of a thought experiment than something you would actually see in reality. Unless maybe we'll come to it, but... So another example could be boron, for example. Boron is not very electronegative and typically carries an empty p orbital. This can be the LUMO. So that would be one example to keep your eye on. Is I would say that is kind of the other quote unquote got you, is that sometimes you'll see a boom, 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 boom. Oops, that's not what I want. So if this is boron's electron configuration, it has 2 electrons in the s orbital and 1 electron in the p orbital. And so when this thing kind of goes to form bonds with things, let me see if I can find a good example of it. Let's say BH3 orbital MO diagram. Okay, so boron, great, 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 and but it is a little complicated. It's more, it's going to involve some interesting. See if we can find a more simplified version of it. Because now it's like this is kind of taking it's seen behind the curtain a little bit, that things are a little bit more complicated than we had first let on. Let's just see if I can just show us a picture. Boron p orbital LUMO. Oh, that's not quite what I want either. This is the most simplified version of it that we can kind of talk about. So this would be an example of it's not even that it's a it's not a sigma star or a pi star. There are situations where the other got you could be, well, an empty p orbital. I guess, you know what? This is the carbocation example. Why am I worried about boron? This is the E1 reaction. That empty p orbital, that could be the most interesting part of a reaction. Or part of a molecule. If you have a molecule that looks like, you know, I could make you guys argue, for example, like let's say we do have this molecule here. And so, like, I could draw this one, and yes, you know, it is more of just a thought experiment one, but the question here is like, well, what is the LUMO here? Is it possible, again, that a sigma star can be a LUMO versus a C double O pi star. And even this example, to some degree, I could say, well, maybe this one technically is still the LUMO, possibly. But think about how to access this LUMO. If we think about the collision theory, to actually hit this orbital, or sorry, to fill this carbonyl's orbital, right? I'm not doing a good job of showing what it looks like, but there is a bunch of CH3s in the way. And so to actually smack into this thing might be kind of difficult to do in reality. And so if I made you argue for, well, you know, what is the reactive part of this? What is the LUMO on this? Or maybe what is the reactive orbital? I could ask you, right? It might be just that it's this one leaves, the bromine leaves with the electrons after the solvent starts to solvate it, and it leaves behind a carbocation that is thought of after sp2 hybridizes to a p orbital. And so it's like, okay, what is it? Is it that the bromine's going to leave and that we're going to have this p orbital? Is that kind of the first step of this molecule just existing? Is because, and I could make it even more likely by putting, like, what if I put hyperconjugation all around this thing? And I was like, oh yeah, look at this. This is a super stable through electron, you know, hyperconjugation. And now chemdraw's just getting mad because I have too many methyls together. So it's likely you can't even make this thing. But like, okay, yeah, I got tons of them all over the place, and they're all going to start stabilizing what was once a bromine bond. Going there and there. Gosh, these are ugly. And so not the best picture, but, you know, again, if I look at the orbitals here, it's like, well, I have a C here, and this C is the 2p, and then I have the oxygens 2p, and so all I'm doing is, where's my paint? All right, all I'm doing is remaking what he did here. Get out of here, you. I'm just remaking, all right, this part of the thing here. And so now I forgot where I was. Was I in here? Yes, I was. Great. So again, I'm kind of doing the same thing that we already did here. This is the O's 2p. So we got this, and then again we can kind of go down, we can go over, we can go up. And in this one as well, go up, go over. And so we have same thing we saw here, like these electrons will now go into there, and so we do have some homo of something to think about. But as well, we now have so let's put that over there because that's describing the double bond part, or the part of this molecule. Nope, not that. Question, just for clarification, you use the TP orbital when forming pi molecular bond orbitals and sp hybrid orbitals for when you are forming the sigma molecular orbitals. Yes, but hydrogen brings an s orbital. That is, I think, the most common got you question, is when you think about the CH bond, The C is bringing an sp orbital of some type, sp3, sp2, sp, but the H is just bringing a 1s orbital. So the H does not bring a hybrid orbital because it has nothing to hybridize with. It is a 1s1. So, but okay, back to this little discussion here. So let me get this little thing highlighted with some red Z. Yes, red Z, baby. Okay, okay. And your boy be pulling out this idea. So let's go back to looking at this molecule as is for a second. And we'll throw out the bromine again. And it's pretty bad because this is a complicated little molecule. Get you out of there, my friend. You are not an H, but okay, great, 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 great. So now I want to talk about this bond here, and let's make this one in blue. And so we know that the carbon is sp3 hybridized, and so we're talking about something that has more S character in it. So I'm purposely saying this is a sp3 carbon that I have purposely put lower in energy than the 2p1. So it's lower in energy over here. And then the bromine, if we go back to our electron, where is it? Not this one, but this one here. Bromine is at 2.96. Okay, so oxygen is more electronegative than it, 2.96. And so, but here's the thing. So let me pause for a second. It's like, all right, so in theory, oxygen is lower than it. So part of me wants to just right away put it here. But I could do a Dr. W thing and say, hint, the hint is that the bromine and carbon has a lot of electron repulsion from the large halogen. The size of the overlap makes for less good overlap in general. Or I could say that well, let me look at all the things we can argue before I just start making stuff up. Oh, boy. So going back to the day 5 PowerPoint. Oh boy, oh boy. If we go back to this one here, kaboom. So we have in this case the electronegativity for oxygen is a little bit lower. In general, the carbon sp3 is a little bit higher in energy, or sorry, lower in energy than the p orbital, so that's what brought the carbon down. And then if we look at the overlap, the low percent orbital overlap also means that these things are a little bit, they shouldn't be as similar in energy as we might suspect that they're going to be. So just for clarification, you use the 2p orbital when forming, or I think I already answered this. Yes, I did. So again, where this bromine orbital is, if it is something where it's like, well, the electrons that we use to bond with the carbon, let's pull all this up just a bit. Well, if this is one of those bonds where they do overlap, let's say, if we put the electronegativity where it was and we considered nothing about size, or we said that the size made it so that the overlap wasn't very good, maybe we would have a LUMO like this and a HOMO, or not a HOMO, but a bonding orbital like this. And so this would not be a LUMO. So this is if bromine is the electronegative and the orbitals don't get close enough due to their size. I think that would be a perfectly reasonable thing to say. Or you could say that, well, because bromine is so big, the size of bromine, right? If we go back to our kind of ideas about what does stabilize electrons in bond, and granted this is for ions, but still applies to why the bromine leaves, or the example we went on earlier in the office hour. Because it's larger, has more protons, has more orbitals, more space for the electrons. It's not just electronegativity. The argument doesn't just have to be electronegativity. If we do a more size-based argument, maybe that brings bromine down a little bit, which would then bring this down a little bit, which would bring this kind of down, and this would now be a little bit wider of a jump down, and let's kind of move this over to there. And this would then also come down a little bit as well. And so once again, it is possible that the first reaction for this is that it's an internal, that this electrons, as this gets solvated, if this gets solvated enough that it takes the electrons with it and goes off with them and leaves behind a carbon that's sp3 and then suddenly goes sp2 hybridized, so it gets to be a little bit more s character, so it goes down a little bit in energy. Like there is some arguments I think to be made for why these electrons could leave the system, and then we could have reactivity here at the carbon here. And you could also add the argument that, like, actually hitting this orbital through collision theory, because I've made it so sterically bulky, yes, it is energetically possible. There is a low line LUMO that might be easier to access than the CBR one, depending on where we do end up putting this in relation to the O1. But again, I'll either give you data or give you some clarity on what the computer said, rather than us making, all these like weird molecules and then me having you tell me with confidence which one is right, because I don't necessarily think you can do that in this example. But I'm willing to say this is one of those examples where it's like, once again, maybe I've found another kind of exception to the rule, but it's a very specific molecule with a lot of steric hindrance and a lot of hyperconjugation to help the bromine leave. And so which one is the LUMO? I think there could be arguments for both of these things. So I will basically, leave that there for now and keep adding to the PowerPoint and keep an eye on the chat. All right, that makes a lot of sense. Thank you. And one more thing. How do you know how much the atomic orbitals drop or rise in energy when they are combined to create a molecular orbital? Sure. So, so again, what's kind of weird about this whole discussion? Well, let me just show you a second. Really, the main thing that matters. Oh, that's not even a good picture. What happened to the internet? The internet used to be good, and then someone ruined it. Now there's nothing good on it anymore. Back when I was your age, we used to Google things and the right answer came up. Now it's like horse shit all over the place. Ugly, 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 ugly. Less ugly. Okay, I can add to this one. This one isn't perfect, but it's good enough. It does most of the work for me. I need another one of these. I got what you need. So it's going to be kind of ugly and kind of whatever. But in this case, this looks like this was a carbon that at one point was bringing its 2s and 2p electrons in. And so there should be 4 electrons here, but it went sp2 hybridized. So how do you know if the atomic orbitals drop or rise in energy? Well, it's about the percent S character, weirdly enough. So it's like here it is 33%. Oh, come on. Give me some text, please. Bow down. And so that energy level is completely arbitrarily set here, or set here, right? Whatever this is here. And then up here, this is 100% p orbital. And so if that's 66, then this would be 33% p. Oops. 33% p, and then maybe that would be the true s orbital. And so we brought ourselves and so before, jeez, how am I so tired? Bum 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 bum. And so again, we kind of have here the s orbital. Oops. The s orbital, the 2s orbital carrying 2 electrons, and then there was also the p electrons, so there is the 2p 2 electrons here and there that are being filled, and these combine together where the 2p orbitals do get stabilized by becoming more like an s orbital, and then the 2s electrons become destabilized by being with each other. And why we know this is true and why we know this happens is kind of what I was saying earlier, where it's like, well, this is kind of interesting because if I have my 2 electrons in the s orbital and I have these open ones up here, why do I get 4 bonds with carbon? It looks like this doesn't really want to bond with anything because it's already got 2 electrons, and so it doesn't seem to be open to accept an electron. Whereas up here, this is like, well, we can accept 1, 2, 3. Well, not even. We can accept maybe 2 things. And so we were like, well, something's off about what's going on with these orbitals. They must be combined with one another. And so hybrid orbitals from atomic orbitals basically means the s gets destabilized and the p gets stabilized. And I'm still trying to figure out, like, yeah, okay, this is kind of another picture of it in some ways. And so, all right, what's happening is an electron is getting excited into a p orbital, and then to stabilize everything, it starts to hybridize. And why does it do this? Well, it gets to be in its own orbital, and it gets to be oriented with the rest of them. And so there's some, theory there behind those electrons doing that kind of stuff. And then the orbitals will combine with each other to form, an sp2 hybrid and maybe a 2pz left over if it's going to form a pi bond with something. But yeah, so it's like, I would say the answer to your question is that the hybrid orbitals are destabilized from the s portion, but stabilizing the p portion of these electrons. Oh, wait, is that what he's asking? No, that's not what you're necessarily asking. You're asking, how do we know how much the atomic orbitals drop or rise in energy when they are combined to create molecular orbitals? That's a little bit more foggy. I would say in general, it's like, if it's the same atom but we don't have lone pairs. So example, in carbon, right, we could kind of say, it's pretty dang good, and so the antibody is pretty dang bad. And if we have C, and then if we have C and O in this case, this overlap is a little bit, quote unquote, this O is a little bit lower than the other carbon, so it should bring us down a little bit more. And our LUMO for this one is a little bit closer to the C. It's almost like what it's doing is when I take this part of the orbital diagram and I turn it into an O, I'm really grabbing this whole thing and kind of smushing it down. It brings down the energy of that orbital because the O has more, would you believe it, protons. And so the protons in oxygen are what are bringing down the energy of the HOMO. And so as you bring down the energy of the HOMO, the LUMO follows after it. And so that is how I use electronegativity to decide how far the orbitals go up and down. Then the other thing to consider, the Dr. Weinschenk example of in his quiz about how the oxygens have bad overlap, that would be kind of saying, so I have the COB, or when I have this O kind of coming in and bringing things down in energy. However, when we had the, whatever the O, we'll go back to his example, the OO example. It's like these ones are the same energy, but because their electron repulsion is high, the electrons that are actually bonding them together are not that stable because these things are not getting close to one another, and so it's not quite as stable. What I was gonna say something, but now I forgot. What are you thinking about? It was something to do with size. Of what, though? I can't remember. I had something that went out of my brain. Dang, my ADHD would truly be. So I'll put that up there for now. But electronegative atoms do bring us down in energy naturally. And then the large size of an atom that is also electronegative not only brings us down necessarily in energy, but the amount of stabilization we gain. So like a good example would be, so CO does a good job stabilizing us. But let's think about CBr. And for whatever reason, we'll also say it's like, maybe we'll just bring it down just a touch more than oxygen was. And so although they are similar in so this is CO, and this is CBr. Because these things don't overlap very well, you're going to get even less overlap here. And so this is going back to that O example, I would say. So, boom. Another little kind of discussion. Explain the difference between an atomic and molecular orbital. Explain the difference between an atomic and molecular orbital. What would be a way to ask this question in an interesting way? So, I can't bring this over to the screen because it has student names on it, but I'm going through midterm review questions and trying to think about questions I could add for you guys to consider and even look at tomorrow to some degree. But obviously tonight's like the last big night for getting it in your brain and sleeping on it. But because it's open, whatever. That answers my question perfectly. Thanks for all your help. Anytime, mister. Come on back with more chemistry questions when you got them. Okay, let's get back to thinking. So for now, I'm just going to kind of close my, quote unquote, close my office door again. So I'll just type this in here. Just knock, bringing screen back to my blah, 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 my main screen with student names. So I'm still here, but I want to work on my main screen rather than my weird off screen. and I need to post to Canvas what we talked about here. So I'm going to do that first. Make sure you can hear me. Okay. So, hi, I was wondering why one electron in an antibonding orbital has a stabilizing effect instead of a destabilizing effect. Can you share the resource that is convincing you of that? Because I would, maybe it's a 3 electron bond, some sort of special situation. That seems funky to me. It seems like the bond order wouldn't be 2, but would be 1.5. So I don't think it is a stabilizing effect. I think it is destabilizing. Let's see what I can find in my searching. 1 electron in antibonding stabilizing. Yeah, I just disagree with the statement right now. Let me keep looking, though. But I love you even though you hate. But still, so good you're thinking about this stuff. It's like, yes, let's go. At least you got some orbital thoughts going on. Find it was in QTP answer key. Okay, great. Let me then start looking at where would it be. Love you even though you hate me. I'm breaking it down. Nice. Very nice. Even used to be together. Pop, pop. No, I don't want to delete that. Come back. Okay. Question QTP 3, question 11. Going now. Bum, 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 bum. Guess you think you never so bye-bye. Honey. Question 11. Okay, if a filled atomic orbital, let me see. If a filled atomic orbital, so let's draw this a second. If a filled atomic orbital, so I have some filled atomic orbital mixed with a half-filled atomic orbital, would you expect the interaction to be stabilizing or destabilizing? Hmm. I'm trying to do math in my head a second. Okay, so it looks like bet you never so bye-bye. So let's say this is 5, or even better, I don't know, let's say it's like -5, and this one is also -5. So together these are -15 energy, and then when we go and bond together, these electrons we'll say are -20, or no, sorry, -10. They've gained -5, and 2 go down here. Hey, 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 hey. B4, and -10 is -20 here. But then we also have one that goes and gets destabilized. So 1 electron goes, and you do everything now, honey. Okay, just to make sure, I'm pretty sure, I think it always has to be... Sorry, this is because I have to think in these numbers. You may hate what I'm doing right now, but I just need this right now. So, let me try it this way. So, okay, -10 goes to, so it was -20 before, then it comes down here, goes down to -15, and both these are -30, whereas this one is at -5 now. And so overall, I guess my negatives are... No, wait. This is -30 before, -30 for 2, -5 for 1. And so, yes, it is overall stabilizing. You are gaining, in terms of energy, -5. And once you go Oh, but what about if I brought two electrons in and I put them together? It would be negative 10. So is this logic even good? Not necessarily. Well, negative 10, negative 25, negative 15. I'm still not comfortable with this yet. Because if I follow the logic through and I add another electron to it, then it would be well, let me just do it. So we'll copy it. In bed with your two. Okay, so get rid of you. Boom, boom. And so now it would be negative 40. I think this might work. Negative 30, negative 10. And so now that I've added the second one in, now that this and this are at... This is at negative 40, so I am where I'm at where I was before. So now I would say, like, okay, yeah, once you have the second electron, you're back to the same negative 40, whereas over here, we were negative 30 before. We got our negative 30 back by bonding down the two electrons, and we are still getting a negative 5 for above, but overall, our overall energy of electrons is lower because we sent two down and only one up. So now let's focus on your question. Hi, I was wondering why one electron in an antibond was a stabilizing effect instead of a destabilizing effect. So why is it stabilizing? Like, here's why I think it's stabilizing. So kind of I think what this question is maybe picking at a little bit is when we're over here, and I want to kind of take some colors a second. Standing here at the bar. You with the cowboy blue. Yeah, Okay. So again, what's kind of happening here is before the electron bonds, there's some atom out here that's holding these two electrons, and these two electrons are only supported by, for sake of argument, let's say, two protons. So over here, these two red electrons are helped by two protons. And then over here, as I bring this one over here, this is one electron supported by one proton. Is that fair to say? I'll let it go for now. There's a part of me that wants to make it two protons and say the other proton, and say the other electron is bonding elsewhere. But I think to keep it simple, what I'm trying to point out here is that when they come together, when I bring this one proton in and I bring these two protons in, that's what causes this to go down in energy. That's what causes this to go down here, is because originally it only had two protons stabilizing it. But when we form this, even though, yes, we send one electron up to the antibond, we get the 2 bond here. So, okay, 4302, what do you think about that explanation as it's because we have 3 protons for these 2 electrons that they're stable? And yes, this one is destabilized. The glue is not in the right location, but the theory would be that the placement of 3 protons is what's stabilizing the 2. So I'll leave that be for 4302 if you like that. Whoa. On the practice test question 6, let me move to that unless I see something from 4032 as I'm moving over. And let me make a note. What time is it? 4:32, so let's make a note. talked about stabilization of 3-electron bond. It is, I guess, stabilization of a 3-electron bond in some ways. Okay. Do it for ourselves. I don't hate you, babe. It's worse than that. Okay, going to exam, pulling it up. And we're looking at question 6. Okay. On question 6, where B is more acidic than D, when D is the proton that through resonance structure is the easiest to get the negative charge on the N. Ha! Yes! I love this question because it's giving me ideas for test questions in some ways, because it doesn't get the negative it does not get the negative actually to the nitrogen. So let me prove to you why it does in a second. So we'll take this molecule and just remake it here. Adored and sad, I've been building up this thing for months. Oh, come on, ChemDraw, you can do it. Ugh. This program actually makes me throw up sometimes, but it is good other times too. It's like, ugh, it's gross. Okay. Here's the gotcha. So why is it that it's a perspective issue? This proton, I get what you're thinking, because you're thinking on paper. You're not thinking in 3D yet, and that's okay, because I've been thinking in 3D for too long. Not too long, long enough. But what I realize is that, to me, I kind of see that this looks like this. So my mind planarizes this molecule. Why is that important? Because where is the pi bond? The pi bond is above and below. Oof, that's really ugly, but helps a little bit. It's above and below. And so what I'm wondering is, you probably did this as a student, and I completely love that you pulled out a pencil and you saw this, and you saw something that you thought was the pattern I was even talking about, because you removed the H and said, where do these electrons go? You know, I removed the H, these electrons have to go somewhere, and so you probably took them and put them on the carbon right here, and that would make sense. Oh, can use a little bit of love tonight. And then you were like, oh, Cam, I see exactly what you were talking about, because you are right. It's like, this is kind of like, if I zoomed in and exactly what I've highlighted, it's what I was talking about. But what I need to let people know is so important is that this atom needs to be sp3. And so really, that's the addition that I need to have to my generic picture to make it a little bit. Here, let me even do the. Let me put it in paint a second, because it'll just be faster. A little bit, pop. So some X atom that is sp3, that is one bond away from some Y atom that is sp2. That is then double bonded to some final atom Z that is also sp2, and Z and Y can equal each other. You know, Z can equal Y. Y doesn't have to equal Z. X can be Y. X can be Z. I mean, there's so many different things. These can be any atom, but what can't change is the hybridization. So let's focus on. Thank you, A, for helping me realize that that's the key to explain this. I knew there was something missing from my explanation, because Zoe was even bringing up that there's something about it that wasn't quite making sense. And she was right. I just hadn't figured it out yet. So, okay, back to this. This carbon needs to be sp3. Why? Because I completely understand that based on what I said in class, it makes a lot of sense for you to take these electrons, put them here, and then put this on nitrogen. I would even give you a decent amount of points to say, like, okay, they're technically wrong, but there's something here where they're moving something quite nicely along with. But if I look over here, if I kind of pull the orbital away from the p orbital, look how they're going up and down the page. And when I take this proton off, I want you to remind yourself that this proton is a dash. When I grabbed, let's get these a little bit smaller again because they're just a little bit too big. When I grabbed this molecule and started to kind of pull on it and put that H into the back of my computer, behind my computer, so I'm tapping the back of my webcam is where it is. That is not going up. It's not that the bond is here. The orbital is not here, and the orbital needs to be here to actually get to the other orbital. If they don't align, right, it's not just energy, it's orientation. The problem with the sp2 orbital is that it is orthogonal. It's 90 degrees to it, and so it can't actually, its electrons can't go, they can't just fly up into the other orbital. They are stuck in an sp2 orbital that is planar. So let me just write this in, text that you could put this text into a large language model and ask it some questions to kind of figure this out. But it's like the D proton, so this is for the problem, so this is for number 6. The D proton leaves an anion in a sp2 orbital. The p orbital is filled with a pi bond, right? That's why the reason that this H is going back is because if these orbitals in pink are describing that bond, then what is describing the green? So those are aligned. Those are parallel orbitals to one another, and they do interact with each other. But let me just delete this because this is not helpful anymore. No, I deleted all of it. Okay, get rid of this. Come back in. Okay, the D proton, which we should say this is like HD. The D proton leaves an anion in an sp2 orbital. The p orbital, and let's name this thing too. Let's name this C1. The D proton leaves an anion in an sp2 orbital on C1. The p orbital on C1 is filled with a pi bond already that is resonating with the pi bond to nitrogen. So because the anion is 90 degrees, gosh, can I spell orthogonal? We'll take it. Or orthogonal, it does not resonate. This is where you really are starting to have to come to terms with knowing where orbitals are on molecules, knowing where pi bonds are, knowing where sp2s are. So I think this answers your question. Okay, that does make sense. Thank you. But that was someone else, so I'll hear from Taras if that made sense. Looking at Gab. Hi, I'm still a little confused with MO diagrams and drawing them, and LUMO HOMO. Absolutely. And I feel like I may have talked about this somewhere already. Let me see if I can find a place I've talked about it. Boom, boom. And once you kind of review this video, come back. Come back tomorrow morning. Come back anytime tomorrow. But I want to know, I feel like I talked about this. Yeah, I did. Awesome. So go ahead and check out the, I can't link it. Go to the announcements, Gab. Go to the announcement. I want you to look for the one that says midterm exam weekend work. You kidding me? You want to look at the timestamps for this. Well, actually, I think I can copy it and send this in. You want to go here. So let me do @Gab. Can I @? I think I can. Yes. Oh my gosh. Look at the internet. No. So check this first and let me know if this helps or hurts, because I've talked about this before with another student who shared the same concerns, and it might not solve your problems, but certainly it'll give you something to talk about with me. And I hope this is the right one. Make sure it is the right one before I send it to you. No, I already did, but boom, boom. Oh no, it is. No, I think it's right. 313.57. 313.57. Yeah, it's right around there. So give that a try, Gab, and come back for me. Going to 432. Should we expect to answer questions about Newman projections? It's not a learning objective, but some. Yes, definitely. So when would a Newman projection be involved? A Newman projection could be involved in an E1 reaction. So for example, let's say I have this thing here, boom, boom, oops, boom, boom, and let's make this ting, ting, ting. What do I want to think here? Bop, 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 bop. Okay. So let's think of a big group. Let's just say it's not really technically that big. So we'll say the T-butyl group is a pretty gosh darn big group. And over here we have another T-butyl group, and then we have little baby H. So I'm making a very clear difference in size of H here, T-butyl over here, and then let's try to make this. I want to make this work real nice, so we're gonna have to get rid of this. Potatoes, bop bop bop. Yoink. And let's make this a CH3. Yes, yes. Ba, 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 da, 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 'cause I want to. Oh boy. You're like, I thought I was done with Newman's, Cam. I thought I was done with Newman's, but you're never done. You are. Once you leave Emory or whatever and you never come back to chemistry, you will never remember any of this stuff. But so let's consider for a second, if I got my little eyeball out, ka-ching, 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 put some, eyelashes on it, and I'm looking down this bond where this is carbon 1, and this is carbon 2. And so my eye is looking, the way I think about it is I kind of literally put my head against the screen, and I know what is the left side of my head, and so this hydrogen is the H of the left of my head, and this H coming out on the wedge is going to be this is the right one. So as I start to draw the Newman projection for this, all right, here is C1, boom, boom. La-da-da-da-da. So this is the H going left, this is the H going right, this is the T-butyl, and this is C1. Stopping you. Oh, Kendra, maybe you aren't so bad, and I'm just, I just need to remember you. Oh, want to. Because weirdly enough, this matters because of a little bit. It builds on what Tara's question was, or Tara's question. So okay, it's not the best Newman projection in the world, but okay. Now let's look behind it. So I see this BR that's in between the left and the right. So that's going straight up. That's where the BR is. And then it looks like the right side has a CH2 going out. So I'll put that out there. And going back into the wall is another T-butyl group. And so we can ask like, let's see. Because my guess is that T-butyl must be bigger than bromine, but let's consider some things. So bromine atomic radii, about 1.1 blah 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 blah. Remind me again. Van der Waals radius is the closest approach for another atom. La 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 la. Me. All right, let's take the bigger one. I'm fine with that. Okay, so this is 183 picometers. And then I want to look at, in a T-butyl group, although we have to deal with, like, I think we have to do some freaking trigonometry. But let's just say, maybe we can get a guess. T-butyl group radii. Oh. No. Okay, instead of this, let's just say, what is a CH bond length? Okay, about 1 angstrom, or... Isn't that 109? Sorry, my mind is a sieve. I think these are the same-ish. 1.91. Yeah, okay, wow. So I would say the tert-butyl group is definitely bigger than bromine. If just the, let's remind ourselves what the tert-butyl group looks like for a second. So tert-butyl group is a CH3 that has 3 methyls off it that all have CH3. So yeah, I would say that if the CH bond is already starting to, it's not quite as big, but it's about 1.09 angstrom, and this is 1.9 angstrom. Like, yeah, I would say then that the CC bond, the other CC bond, the other CH bond, it's definitely a bigger group. So what we want to do is look at the conformers that could be happening for this Newman projection. Man, this is a mess. Am I always later and keep on getting better? My mom's here too, calling up my best friend. Okay, modify existing. So we're back to the Newman world, and we're kind of like, oh, dang. So, Cam, you tried to, like, write that molecule, but in reality, or not in reality, that's not the right way to talk about this, but molecules are constantly tumbling through space. They're rotating and moving. And so the most stable form, though, would have these big sons of bitches as far away from each other as possible. And so we're going to go ahead and move the T-butyl group up here. We're going to rotate the back of this. So I'm going to put the T-butyl group back here. Put the bromine group here. Put the CH3 group here. And now I have this stable Newman projection of this molecule. And what I want to point out to you now is that, okay, what does this mean in terms of why did I do this? Because it has to have something to do with the E1 reaction, or he wouldn't bring it up. And that's because, okay, let's now redraw what happened. So I took my T-butyl group and I moved it up here. My days I've been cradled to the grave. That's such a sad song. Okay, stop being sad. Don't be sad. Be happy. So now I've adjusted my line structure to match the most likely way I'm going to find this molecule. Now, this doesn't have to be the case, and this molecule can turn to the other conformations we saw. But this bromine at some point is going to leave the system. And so that's the first step of the E1 reaction. So this thing leaves. Steric hindrance, if it is trans more stable. Well, that's kind of what we're going to start looking at, right? So we're going to unpull this off. Once this comes off, let's think about what happens. So it leaves the electrons behind, and the electrons are left on here. Or sorry, they're not. What am I just saying? They're not. And so we're left with a p orbital and a positive sign here. And so now the orbital here needs to sp2 hybridize because that is the stablest form of it. And so the this orbital will try to make these other ones go into a formation. And so let's think about what that would look like. As that orbital leaves, we'll go sp3. And so now, how does that change our Newman? So I'll kind of say, well, back here, we still have sp3 out here. But if I look back now at the back carbon, these bromines aren't here anymore. So that's gone. And now my T-butyl is... Gosh, this is so ugly looking, but it's like, this is kind of where the T-butyl is now, and I know it's so ugly. And I'll try to transfer it to a line structure as well. But it's back there. And same thing with the CH3, it's also now going back. Years ago, by my grandmama, rest her soul. CH3. Never grow old. Okay, because now let's try and redraw it again. And where the p orbital is, how do I put it behind? I need to figure that out. What if I leave this here and copy and paste? Will it just do it for me? Not quite. Baby, I'm not a rose, I'm a well. Send back? Doesn't really work, but it's back there on the carbon behind there. So arguably, I kind of want to make it a little bit smaller, but it's like behind it. It's on the back carbon. And so when we go back and look at the line structure again, we can kind of think of it like I'm going to rotate it just a little bit. And now it kind of looks like that. Got that gypsy blood, always chasing thunder. And so now we have the p orbital right there. And so the question that I would ask you guys is, does it react in this conformation? Does it need to rotate, or is this going to react? Like, let's kind of keep thinking here. So let's follow our tracks here. So we basically said, we rotated the molecule to make it more stable. The bromine left. It sp2 hybridized. And then I drew it as a line structure down here. Now, is it ready to react? Is it ready for a base? Is it ready for a base to react? And let me answer this question by asking you a question you might know the answer of. What does this result in? What is the functional group that an E1 reaction results in? What is my final result going to be? Because if we draw the final result, we might be able to answer the question I'm asking here. So I'll start kind of getting a little bit of a guess of what is the final functional group that comes out of this. And you can be wrong. Like what is the purpose of an E1 reaction? We go from a halogen, an alkyl halogen, to what group that we put EZ isomers that we associate with? And the bad times makes me happy, makes me sad, that nothing lasts forever. I'll keep running. Exactly, alkene. It goes to an alkene. And so one of these H's has to go away because we go to, this becomes wedged. And so the electrons that we're removing, let's be real specific. Yikes. Baby, I'm not a rose, I'm a wildflower. So I'm chasing thunder. So again, just follow me for a second here. This is LUMO. LUMO, empty. And gosh, this is so pretty. I just love drawing this stuff because it all makes sense. So let's label it. So LUMO. Yeah, I remember. Little bit of pink. Pink. Okay, So this is at some energy level. We're just going to kind of set it there. Now, over here, there is a an s orbital that is bonding with a sp3 orbital. And so these are overlapping. And what happens when this OH comes over here, it does not pick off any electrons. It merely takes the proton away. And this combines, oh, this is not right. This is not right. Sorry, this is not good orbital overlap. That's anti-bonding, Cam. I know. I'll fix it. Friends the summer. There we go. Now we got some bonding. So that explains why it actually bonds. But what I want you to realize is that once I remove this proton, the wave function is going to change a little bit. And we have to ask ourselves, is it ready to align like we see down here? Notice how these are in a pi bond. The reason a pi bond is a pi bond is because it's parallel with one another. The p orbitals are parallel with one another here and here. They're parallel with one another. But what I want to ask you is, or what I want you to start considering, is this wedged bond, is this parallel with the pink orbital? If it's coming out of your screen and this CH3 is coming out of your screen, if this comes out of your screen, is it aligned right now correctly with the orbital? The answer is no, it's not. Which one is? It's this one down here. Because this is on the page. This one is 2 sp orbitals. Gosh, I love chemistry. Oh, I love it. Your timeline, the spirit. Exactly, it's parallel with this. So it's like, wait a second, how do I get these electrons to go? Because they won't leave. The reason they won't leave is you're not picking off the carbon in the T-butyl. A base is not coming to attack the carbon in the T-butyl, it's coming to look for hydrogen. So what has to happen is, no, the reaction doesn't happen yet, not because the energy gaps aren't ready. This is what's so important about this, like, midterm one. I wish I could, like, let everybody hear this. You are so focused sometimes as students, understandably, because you're left so much in the MO orbital. For sake of argument, we know an sp orbital is lower in energy, so I'm going to put this red one down. And so right now, if I have, like, let's even bring this out for a second. Right, this orbital here, as I start to see that it is all right, so let's make that bond to H, and we're going to say these are when these combine, we got an s orbital, that's great, we got an sp orbital, so it's lower in energy. So you might say, oh, Cam, look it, they're close in energy, so I'm going to bond into the alkene. I got you covered, dude, because I know I'm so smart, and you guys are so smart. That's why you're here. There's 2 electrons in here. Those 2 electrons are here, and so we're about to form an alkene because we know that that's what the mechanism says we make, and so they mix, and then down here, these 2 electrons form, right, what you are. Where did I put it? Did I delete it? Yeah, I did. Well, let's just go up here. Going out tonight with bum 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 bum. Okay, getting rid of this and making this a double bond. And does this still work? Is it Control Shift clean? Yes, kind of. Yes, there it is. That's the final product. That's where we get to. This bond down here, this, let's highlight this guy. Green. I know this is not pretty, but just have to deal with it for now. Until one day, maybe he'll actually make a video. I will when I'm ready. And you feel it. So, we have donated 2 electrons that were connecting the carbon, or the hydrogen to the carbon. And we've donated them to the empty LUMO, the pink LUMO. And now, I'm going to just say, oh, these 2 electrons are like, yo, bro, great, yo, bro, great energy level. Let me just, boom, I'm going to move down here. But why don't they? This is the biggest got you. I gotta make it bigger because it's such a got you. just because you got the right energy match, these, I gotta think of some nice word, these cats, let's just use the proper word, these orbitals got to align. They need to actually collide. What is the first thing in Chem 150? Or maybe it's Chem 202. Chem 202, day one, collision theory. The only way for the red orbital and the pink orbital to align, not only does their energy, Siri, I know you're listening to this and you love it, but I can't have you listening. The red and the orbital, although their energies match, they need to align, they need to collide. And so what I want to show you now is another adjustment to the Newman projection. What do you notice is that the T-butyl, if this red bond is red parallel to the p orbital behind it, how do I rotate my Newman to get the orbitals to collide and be oriented correctly? I'm feeling a bad, I'm over as hell. What's a... Right. We need to take this Newman projection and say, rotate, please. And where am I going to put the T-butyl? Am I going to put it by the... This is what you were saying, steric hindrance. And careful saying trans, get to E and Z. You would rather go to the E isomer, where the T-butyl shifts this way, because then all it's fighting against is a all it's fighting against is a CH3, and so it goes there, and that puts an H in the right place, where now the orbitals align, and you can snap them together. Exactly, you rotate it. But the other option is, you could have also rotated the T-butyl here instead, moved an H over here, moved the T-butyl here. And this happens. This is part of reality, certainly. But if you had to guess as a student, which one is A, more likely going to be in your reaction flask, or is B? When you isolate this, which one is going to be in higher percentage? Which one is more likely to, what conformer is more stable and will undergo the reaction where it puts the H in the right location? So, I mean, I know everything. Take the time, take the time, take the time. So we just hit them with the 506. Oh, Newman and E1 anti. Oh, it has to all make sense. Yeah, A does. Because if I look at A, it's like, this is, if I think about, you know, old-fashioned whatever chem, whatever it was, it's like A has this energy level, but B has this energy level. Because T-butyl groups, it's like, I know I can use more friendly terms, but I like the aggressive terminology. T-butyls hate each other. It's like, get out of my face. They got big old stuff going on. They're getting all over the place. They are, for lack of a better term in 2025, T-butyls are man-spreaders. They man-spread all over the damn place. Whereas CH3 and H are like, chill out. Can you just, like, take up your own space? And so that causes the energy to go up because they're putting their electrons everywhere and hitting everything. But anyway, so did I answer that question? What was it? Should we expect you to answer questions about Newman projections? Yes, you should. It's not a learning objective, but it has to do with E1 in particular. Do the out-of-class points from week 0 count towards any week that we don't get 5 points in? Yes, they do. Thanks for doing week 0. Thanks for coming to the community early. That makes sense. Thank you. Steric hindrance. Yes, you got that. Alkene. Yes. No, it's parallel. Rotate so HA. Yes. Great. Other new questions? Great, 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 great. Remember, collision theory does not go away. And celery with peanut butter. All right, back to student answer. So I'm going to go back to, you can see me, but I'm going to be working on some student stuff on my main screen. I just don't want to show names. Totally fine. Still not on it yet, but two quick questions. Will the exam be the same length as the practice? How soon will we get scores back? It really, I would say this. It's like, you guys are going to give me some heck of feedback, I'm sure, on this exam because I am really going to challenge myself and say, how do I test these learning objectives knowing how easy it is to put certain questions in a large language model? And so there's going to be part of me that will make like, some of the questions. It's like maybe let's let people get up to 60%, get them up to a 60% score where it's like if they engage with the learning a large language model and maybe sometimes it'll return along a wrong answer and maybe they'll lose a couple of points if they don't check their work. But 60% of your score is like, yeah, a large language model could have got you to 60%. But I want 40% of the test, or maybe we'll say 20 to 30% of the test about asking questions that are very difficult, in my opinion, and I'm ready to be wrong, for a large language model to solve. And then the last 10% will be pushing you beyond the subject, but applying the same foundations of the learning objectives. And that's where I might cut some flack from you guys. So, in the past, I sometimes have had to take questions and been like, yep, I just wrote this so horribly that I'm going to curve it, right? I'm taking this question out, or I'm giving you all these points. I don't know when your scores are going to get back because it depends on what I want to do in terms of grading. If it's all auto graded, maybe it happens right away, but I doubt that's the case. But, there might be a way to do that, but I really doubt it. So my guess is and I have to be careful because I make promises and then I don't fulfill them. So let's say for sure by next week, Friday, but I expect to get them back much sooner than that. Um, if I'm on top of my stuff and I design the test right, I'd love to get it back to you guys Friday night, Saturday sometime, Sunday later. But I'm going to give myself the understanding that I'm biting off a lot I can't chew right now, but I want to chew it all. So, anyways, that's the answer for now. Is office hour engagement supposed to be documented for online engagement? That works. Absolutely. It can be. And the good news is this should live forever. When people come back and watch this video next semester, this conversation with this person should still exist. And that's what's so cool about the online world. It's like, oh my gosh, how have I not been doing this? Things are recorded just naturally and shared naturally. So, yep, this counts. Thank you for being here. Thank you for asking a question. Thank you for being engaged. Thank you for answering my questions as best as you could, whether they were right or wrong. They were all right, but doesn't matter. Just talk to me. God, is that so wrong to talk about chemistry? I love it. With the blood reaching in an endless cycle of just death with no defendants. Action and is exciting, but Jesus beneath. And I've been reading and writing. Are we a nation of states? What's the state of our nation? Thinking past tomorrow. I don't think I'm showing anything. Let me see. Am I showing anything? No, we're good. Yes! Good for you, 432. The only thing 432 you want to do is when you submit this, just black out your number. Yes, I could go back and figure out who it is if I cared. Yes, it's not truly completely blind experiment, but I don't care. I mean, I do care, but I don't care. I wouldn't go looking. But just be aware that, in my opinion, I would block out your number just so I don't associate like, oh, that person is that number. Yes, I could go looking for it, but I won't. Up to you. If you're fine with me knowing who 432 is, go crazy. But that's your choice to make. I won't go hunting for it. To see our glory, I may not live to see our glory. Gladly join the fight. We'll gladly join the fight when our children tell our story. They'll tell the story of tonight. Gosh, these are ugly. They're technically dashes, so where would the... I guess it would be going wedged and coming out. Something they will never take away, no matter what they tell you. A glass to the four of us. Tomorrow there'll be more of us. Telling the story of tonight. Oof, oof. Story of tonight. Alright, what are we trying to show here? Why does this not work? No matter what they tell you. To the four of us. Tomorrow there'll be more of us. Telling the story of tonight. And maybe I can answer it more simply. Tell the story of tonight. Folks love more than going downtown and slumming it with the poor. All right, let's make this green for correct. Daughters Peggy, Angelica, Eliza slipping to the city just to watch all the guys at work. Angelica, Eliza, and Peggy. Daddy doesn't need to know not to go downtown. Like I said, you're free to go, but look around, look around. Ouch, ouch, ouch. Daddy wants to join the war, crowding in the square. Now there'll be violence on our new ideas in the air. Look around, look around. Remind me what we're looking for. She's looking for me, Eliza. I'm looking for mind and work, work. Work, work. Oh, wow. Like from in the city, someone understanding, someone looking. Excuse me, miss, I know it's not funny, but your perfume smells like your daddy's got money. Okay, that one goes there. Why? Because these orbitals can, not perfect alignment, but good enough that they can align. So how do I need to write that? Not really. So that makes sense. Then this one is being I guess in a way, it's technically engaging with its pi star. The yellow's pi star is being filled by the red and making a pi bond while breaking this bond, leaving behind electrons in a p orbital. Would I sp3 hybridize it? I feel like I would. Yeah, I definitely would. Because I want to get it as far away from other things as possible. If it was a cation, I wouldn't care. So I do sp3 hybridize it. So let's show that one step at a time. To be self-evident that all men are created equal. Look around at how lucky we are to be alive right now. And happen, and we're happen. Work, looking for a mind and work. And this will answer their question. But why, child, why? Hear ye, Samuel Sebring, I present 3 thoughts on the Continental Congress. Heed not the rabble who screams revolution. They have not your interest at heart. Oh my God, tear this dude apart. House and bloodshed are not a solution. Let's change these. They're playing a dangerous game. I pray this showed you his mercy. For shame. For shame. He'd have you all unravel at the sound screams, but the revolution is coming. I've not gone to Windress. It's hard to listen to you with a straight face. Chaos and bloodshed are not. I shouldn't call the Lumo. Let's just say the Pi Star, because we don't know if it's the Lumo. Could it be the Lumo? Almost certainly it's the Lumo because it's a pi. The danger, strangely, your mange is the same. Red arrow, okay, to fill pi star of yellow pi bond, breaking it and making new pi bond with red electrons between O and C1. So let's label these. Don't modulate the key, then not debate with me. Why should a tiny island across the sea regulate the price of tea? Alexander, please. I'd rather be decisive than indecisive. Drop the niceties. Price of my love, not a price that you're willing to pay. And this works for me, but does it work for other people? I don't know. Why so sad? We made an arrangement when you went away. I'm your man. It's like, how the heck do I even show this? Be back. Soon you'll see. Let's get those at least a little bit better aligned. You belong to me. I'll be back. Time will tell. You'll remember that I served you well. Oh, it's not great, but it kind of is working. And when push comes to shove. Yuck, yuck, yuck. Alright. My love. It's kind of back there, and that one's like kind of also back there, though. You say our love is draining and you can't go on. Ugh, pretty bad, pretty bad. Oh, but you're my favorite subjects. My sweet, submissive subjects. My loyal, royal subjects. Forever and ever and ever and ever and ever. Like before. Alright, we'll just have to deal with it. Swing push. Yeah, da 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 da. What is that? Oh, it's that. I'm so goofy. 1,000 troops in New York Harbor. Oh, Lord. Oh, Lord. Glory, rise up. Fight for this land. There's only one man who can give us a command if we can rise up. It's the only way to rise up. Rise up. Here comes the general. Moment you've been working for. Here comes the general. George Washington. Nice. Make an all-out stand. You know I'm gonna need a right-hand man. Can I be real a second? For just a millisecond? God, and tell the people how I feel a second. How do I represent this without being totally horrible? Oh, that works poorly. Gosh, we need to do different angles. We need to constantly be able to change our angle on these things. Oh, I need to find a better program than ChemDraw. ChemDraw will work, and I could do it. I have to be very careful with how I do it, but it could work. Outmanned, outnumbered, outplanned, all outstand. I'm gonna need a right-hand man. So we got these two little electrons, which are the yellow ones. Let's make them green, though, just so we really catch their attention. Let's do the cannons. Shaboom goes the cannons. Watch the blood in your shit spray, and boom. They're abandoning Kip's Bay. Boom. Don't like that orbit or that arrow set. Yuck, 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 yuck. No, no, we're not doing radicals. Please, God, no. With a giant to lead America? Distant. I cannot be everywhere at once, people. I need of some assistance. It's not the best orbital. Aaron Burr, sir. As you were, sir. Until he caught a bullet in Quebec. Well, in summary, be of some assistance. how you keep firing at the British from a distance? A couple of suggestions. Okay, yoink. Ho ho ho. Have you met Bert? Yes, sir. We keep meeting. I wonder if I can make this work somehow. There's nothing wrong, sir. On the contrary. No, I can. Maybe this works. Oh, Lord. No! Wait, maybe. Okay, I think it might work. You're a great man with much renown. Flanders cannons when you were still downtown. To be their secretary? I don't think so. Upset? I'm not. Dying is easy, young man. Living is harder. Ka-ching. Ka-ching. And then we need to show the result. And let's think how normal human beings think. And in this direction, how about we don't confuse students to oblivion? We are outgunned, outmanned. That's true. 80, a winter's ball. Oh, this should be shaded. It a question of if Burr or which one. Can I flip these? Oh. Now it doesn't have to be shaded. Boy, you got me helpless. Eyes in the sky's the limit, I'm helpless. Counting, I'm drowning in them. We were at a rebel with some rebels on a hot night. Okay, red electrons collide with pi star. Orbital and break. I'm gonna break it. Breaking. 2. I am so into you. 1 week later, I'm writing a letter nightly. Now I'm better every letter that you write me. I'm just saying, if you really love me, you would share them. In the living room, stressing, blessing. A tolerance for pain, a couple of college credits, and my top-notch brain. Insane. Your family brings out a different side of me. Peggy can rise in me. Angelica trying to take a bite of me. Figure it out. Living around the family. Yes, Allie's coming home. Never be so helpless. I do. 'Cause he lies us in it. To your eyes and the sky's the limit. People are gonna be like, what the heck did you try and draw? Somebody has got to attempt it. Gosh, it's not very good though, is it? Okay, let's do a little red there. Alright, we're seeing some cooking going on, I guess. Alright, let's make sure the orbitals now make sense. A toast to the groom, to the groom, to the groom, to the groom, to the bride, to the bride, to the bride. Jellicoe's always by your side. Your union to the revolution. You strike me as a woman who's never been satisfied. I don't know what you mean. You forget yourself. You're like me. I'm never satisfied. Is that right? I've never been satisfied. Oh, my name's Angelica Schuyler, Alexander Hamilton. Where's your family from? Unimportant, there's a million things I haven't done. Just you wait, just you wait. Oh, it's so bad. It's so bad. It's good. Total agreement. It's a dream minute, a bit of a chance. It's a bit of a costume. It's a bit of a chance. Did you see his answer? He's penniless. He's smelling by the seat of his pants. Handsome boy, does he know beach fuzz, and he can't even grow it. And she is helpless. No, she is helpless, and her eyes are just helpless. 3 fundamental truths at the exact same time. All right, did we do it? Boom, boom. Yeah, we did. Yeah, we did it good enough. Only rich. My father has no son, so I'm the one who has to social climb for once. And I'm the oldest and the wittiest, and the gossip in New York City is, and the cityest. And Anders penniless. Oh, it doesn't mean I want him any less. Skylar. Know my sister like I know my own mind. You will never find anyone as trusting or as kind. And nine is Alexander's eyes. Okay, 1. I think we can leave it as that for now. Live to see our glory. Can get married. All right, I think that's good enough, kiddos. Okay, 1 red arrow. And let's not confuse them. Let's make these black. Just make everything here black. You are the worst, Burr. Between the sinners and the saints, it takes and it takes and it takes, and we keep living anyway. Okay. I am not certain. Hamilton doesn't hesitate. He exhibits no restraint. He takes and he takes and he takes. Come on, give me the fills, please. No, no, can you shade? Can you do anything? All right, fine. Fine, fine, fine. This is going to confuse the hell out of them, but let's just send it. All right, this is the last thing I'm going to answer, and then I'm going to give myself the grace to say, you did some good stuff today, kid. You're good. Let's not put the student name in, so let's just do that. And now we do need to mute our screen. All right, my goal is to... Oh. Okay. Is there a last minute question, perchance, of If you are here with a question, if you may just be viewing this, likely you're watching something old, but I'm gonna go to Twitch, play one Dota game, and then call it a night. So I'm going to my Twitch stream now, and if you